Let me press continue. SAC this year was supposed to be held in the city of Victoria, a very beautiful city on Vancouver Island, just west of Canada's mainland in the Pacific. SAC has never been held in Victoria before, so hopefully when we're past COVID, we'll be able to circle back here sooner than later. So in the next couple of slides, I'm gonna give you some information about the registration stats, the conference format, and how to access the full program as well as the preprints. So we have 121 attendees or registrations with affiliations well spread out. But one thing to notice is that we would expect an academic affiliation or academic institution at the top of this list. But in this case, for this year, we have the Government of Canada. In terms of countries, we have 27 countries represented in this SAC, with Canada and the Netherlands, obviously, lying on the top of the list. So with respect to the conference, the schedule is held over research seminars. It will run for 3 days. Every day we start at 9 a.m. Pacific. So make sure that you have, let me put the laser pointer, you have your time zone displayed in the upper right corner. We have the 3 days, we have talks running for approximately 1 hour. The talks will, every day we will have 2 sessions, and each session will have from 3 to 5 talks. Each talk is 5 minutes, so it's going to be a summary of your results or the speaker's results, and it will be followed by a 10-minute to 15-minute question period moderated by the session chair. In the first 2 days after we finish the paper technical talks, we have 2 invited talks, and on the first day, 2 invited talks on the first 2 days, and on the first day after all the talks are done, we have a social event that is hosted on WonderMe. You should have received the room link in your registration confirmation email. Please feel more than welcome to join in there. So the full program is carried on YouTube. So if you get to our websites in the accepted papers link or page, you can find all the 23 accepted papers along with links to their recorded 20 or 25-minute talk on YouTube, as well as the preprints or the pre-proceedings of the paper. So I guess that's it for me. Andres, do you want to?
Yeah.
Okay.
So a few stats from the program committee. We've got 60 submissions, which was actually a bit more than we expected in the beginning because it started quite slowly. 23 of the papers got accepted, so we've got an acceptance rate this year of about 38%. In total, we ended up with about 190 reviews written by 38 program committee members and with the help of 28 sub-reviewers. Next. And I think our program committee was actually quite well spread. So again, Canada is first, but then afterwards it's well distributed. And I think the only continent or subcontinent that we are missing is South America, but I think we've got some South American people still represented on the committee, which are now migrated somewhere else. So if we would have looked for origin, then probably that would also be well covered. Next. So I would like to thank a lot the program committee that managed to do this. I think the summer was really horrible in terms of the review load that swapped all of us. And still these people managed to find the time to do this. So that was great. Next. I would also like to thank the sub-reviewers, which actually contributed to this next. So eventually we managed to fill a program which I think covers the usual SAC topics. So we've got 2 slots today covering symmetric crypto, from a provable security side up to attacks and constructions. Tomorrow we've got a bigger focus also on post-quantum cryptography, which I think got a bit bigger compared to the last years. And then in the end, on Friday, we've got 2 slots which cover all kinds of different applications and the main topic of this year, which was privacy and technologies. And we're happy that we have 2 invited talks next. So make sure that you don't miss those. Today, Sophia will give a talk on how private is secure messaging. And tomorrow we will have Eyal talking about privacy preserving Bluetooth-based contact tracing. One size does not fit all. And so we hope to see you there and maybe later in the socializing part. And I think that's it from our side. And so at this point, I would like to hand over to Kali, who's chairing the first session.
Yeah, so let me stop sharing my screen so Kelly can, take
Yeah,
it.
hello. Hi, Liam, hi, Andreas. Okay, can you hear me well? Okay.
Yeah.
You hear me
Yeah.
okay? Right. Yes. Okay, so hello everyone. So my name is Kali Mandel. So welcome to the first session of Symmetric Crypto. So there will be 3 talks in this session. You know, as Riha mentioned, I mean those presentations. I mean you can see the presentations are uploaded in YouTube, full presentation. And so basically in this session we will have the short presentation. So each presenter will have 5 minutes to briefly present their work, and then you will have about 10 minutes for the question and answer. So okay, all right. So if you are ready, then we may proceed for the first presentation. So the first presentation, the title of the first presentation is multi-user security of Elephant V2 authenticated encryption mode. And this paper is by Tim Bain, Yulong Chen, Christoph Dubravnik, and Bart Menick. So I believe Bart is presenting. So the screen is yours.
You're muted, Bart.
Thanks. Now you hear me. I was asking, do you hear me? But
now we hear you.
Okay. Yes. Yeah. And yes, I found the problem indeed. I was muted, as you said. Okay. Welcome. It's a great honor to actually give the first presentation. As you correctly mentioned, it's a work with Tim, Yulong, and Christoph, multi-user security of the Elephant V2 authenticated encryption mode. Let me start first by authenticated encryption, just to give a very quick recap. Authenticated encryption is basically just a cryptographic function. It gets us input a key, typically associated data and a message, and it magically turns it into a ciphertext and a tag. And here the ciphertext is an encryption of the message, and the tag authenticates basically the associated data and the message. And the nonce, in this case, is then also used to somehow randomize the scheme in such a way that if you authenticate and encrypt the same associated data and message, but under a different nonce, you should get unrelated ciphertext and tag. And currently, the NIST, the National Institute for Standards and Technology, is organizing a competition, a lightweight cryptography competition. So their goal was mainly authenticated encryption. They also include hashing as an option. And they described that they wanted to have schemes with a minimal security strength of 112 bits of security, at least as long as the data complexity is at most 2 to the 50 bytes. There are some more conditions, but these were the conditions that they wanted the submissions to satisfy. Back in 2019, February 2019, there were 56 first-round candidates. In August, they went to 32 candidates, and in March of this year, they went to the final round with 10 final candidates. And one of these candidates is Elephant. So Elephant is a third round candidate by Tim, Yulong, Christoph, and me. And it's a permutation-based authenticated encryption scheme. However, it's different from the typical permutation-based approach in that it is parallelizable. And our goal was to design a scheme that achieves security. So a scheme that uses the smallest possible permutation while still meeting the security requirements that were dictated by NIST. And this was the scheme what we described in February 2019. So we have a permutation that's typically evaluated in parallel, and it is masked, where the mask is depending on the key K and two parameters 0, 0 to something. So in general, we have a mask on input of the key and parameters A, B. And the mask is computed as permutation on the key, and then two LFSRs, phi1 and phi2, evaluated on this value A and B times respectively. Encryption is simply counter mode technically, but the counter is in the tweak. So we take the nonce. The nonce is going into the permutation calls everywhere, and then the key and the counter are in the mask. So the mask is of the form 0, 0 up to LM minus 1 is 0. So B is always 0. And then the output is a key stream that's added to the message to get a ciphertext. Subsequently, we do authentication. So authentication takes the nonce and associated data, it pads it injectively to get associated data blocks. It also pads the ciphertext injectively to n-bit blocks. And it does the same thing as for encryption, but now with different offsets. So B is in this case 1, a small b in a superscript, and here it is 2. You add these values and then you truncate. Roughly you see that this is an encrypt and MAC design. It's the most secure generic way of building it, where you get ciphertext integrity. You have counter mode encryption, and this is technically a Wiegmann-Carter-Schupp authenticator. It's fully parallelizable. It uses a single permutation P, and it only uses this in a forward direction. And we proved that in the random permutation model, this scheme was secure. So it achieved confidentiality and authenticity against attackers that do not misuse nonces. And in fact, if you misuse the nonce, security fails. Now for the final round, we made a change. So the final round, we have Elephant v2, and it is slightly different. So we have this term here, this primitive call here on the left is now moved to the right. And an additional change is in the role of the mask parameters. So here with these superscripts, the B value used to be 0, now it's 1. Here it used to be 1, now it's 2. And here it used to be 2, now it's 0. The second change is merely cosmetic. The benefit is that we get the mask 0, 0 here. But moving this thing over there technically makes the authenticator a protected countersum authenticator. And we require a different proof for that. And nevertheless, it was claimed that v2 retained all good properties of v1. That means confidentiality and authenticity under the nonce respecting setting, and that in addition, this achieves authenticity under nonce misuse. And now in our work, we analyze the security of Elephant v2. So we give a formal proof that indeed the security guarantees of Elephant version 1, confidentiality and authenticity against nonce-based adversaries, is preserved up to a comparable bound. Elephant version 2 additionally achieves authenticity under nonce misuse. So if you put this in a nice table on the left, we see what we had. Confidentiality and authenticity in the nonce respecting setting only. But now we have the same thing, but in addition, we have nonce misuse authenticity. And finally, all results that we prove hold in the multi-user setting where the attacker has access to multiple schemes. And the number of users actually doesn't really influence the security bound. It only affects minor terms in the bound. The proof and more for that, I would like to refer you to the full presentation or the paper. But this is basically what we did in the work. So thank you for your attention.
Yes, thank you, Bert. So we now move to the next presentation. Yeah, we'll have the question answer at the end of, after all the presentations. So the next presentation is designing S boxes, providing stronger security against differential cryptanalysis for ciphers using byte-wise XOR. So the paper is by Yusuke Todo and Yu Sasaki. And I guess Yusuke will present it. So Yusuke, the floor is yours.
Yes, so can you hear me?
Yes.
Okay, and you can see my presentation.
Oh, yes, I can see it.
Okay, so thank you very much for introduction. My name is Yosuke Todo from NTT Social Informatics Laboratories. As a paper title is like this, so it's a sorry, very long title. Okay, so this is the joint work with Yu Sasaki. Oh, wait. Okay, the topic is how to design nice block cipher. So actually, I think designing nice block cipher is a very big and open question for symmetric cryptographers. And we have very nice design strategies such as S-box-based block cipher. And in S-box-based block cipher, we can design S-box and linear layer independently, usually. Then in that case, we first design nice S-box whose maximum differential probability is as low as possible. And independently, we can design linear layer whose number of active S-boxes is as many as possible. So in that case, so we have nice theory about maximum differential characteristic probability. So like this, so MDCP is lower than MDP to the minimum number of active S-boxes. So this design strategy is very, very nice because it's super simple and we can design S-box and linear layer independently. But of course, there is a possibility we overlook something benefit when we consider the interplay between S-box and linear layer. So we tackle these topics. But of course, this topic itself is not new. For example, so the present is a typical example. So you can see the present round function. So present, each output bit of S-box goes to different S-boxes. So in that case, branch number is super useful because so if branch number is high, we can guarantee many number of active S-boxes. So if the linear layer is present like a design, branch number is very useful. But how about other ciphers? For example, AES-like cipher or Hessel SPN cipher. So in that case, to best of my knowledge, we don't have a nice design criteria for S-box to enhance the security. But of course, so if we focus on the implementation performance, we have some additional criteria for S-box, but from the security aspect, we don't have a nice design criteria considering the interplay between S-box and linear layer. So we tackle this problem. So we have two contributions. The first one is for the extended generalized Fresnel network. Extended GFN was proposed at SAC 2013, and so concrete substantiation was proposed as a LadyPad at the IEEE Transactions on Computer 2016. So this is a round function of LadyPad. So we first have a nonlinear layer similarly to the generalized space-like structures, and we have a block shuffle as the light and as the last. And so we have additional linear layer between the nonlinear and the block shuffle. So this is the main feature of EGFN. So we first analyzed this network and we found high probability identity differential transitions are very important for the security of EGFN. So what is a high probability identity differential transition? So actually, LadyPad S-box allows differential transition from 0x6 to 0x6 with MDP is a 2 to the minus 2. So if S-box allows this type of differential transitions, we find very nice differential characteristics. So if we want to enhance the security, avoiding this differential transition is very useful. So how to avoid, and very, very simple and super easy. So original SBox is like this. And if we replace the last 2 bits, so 2 bits of the output, so we can avoid such high probability identity differential transitions. So this is the DDT. So you can find the original SBox, you find the 0x6 to 0x6, so with MDP, but for new SBox, there is no such differential transition. In that case, now we replace the original SBox with ours, and we compare the MDCT, and this is the result. So blue line is the original, and red line is ours. So we can show using our new SBox, it's always better than original. And as you know, as our change is only this swapping. So I think concerning the hardware and the software implementation, this modification is negligible, and I can maybe, so this modification is very nice to enhance the security. And another contribution is a result for AES-B-MC cipher. So what is AES-B-MC? So as you know, original AES consists of sub-byte rows, mixed grammars, and add round key. But in AES-B-MC, we use binary matrix instead of the MDS matrix in mixed grammars. So this type of design is very common for lightweight block ciphers such as Skinny, Mantis, Midori, and Craft. And in that design, so high probability chain length is very important. So when so what is high probability differential chain length? So when delta 0 to delta 1 is MDP, and if delta 1 to delta 2 is MDP, and so we consider this type connections. So if we don't have any differential transitions with MDP from delta 2, we can say the chain length is 2. And when so there is a nice differential chain whose input and output is the same, then the chain length is infinite. So this is a typical example. Okay, so that now the top one is an original Midori, and the 5-round best differential characteristics. And this is a chain patterns. So we can find a nice nice chains, and whose chain length is infinite. So we have a very nice differential characteristics. But if we use SBox, but chain length is at most 2, we need to use very low we need to use differential transitions whose probability is low. So thanks to this effect, we can guarantee the lower differential probability. So this is a similar result. So the blue one is original and red one is ours. So if we replace original SBox with ours, so we can guarantee the different securities against differential analysis efficiently. Okay, so finally, I want to say the future work and conclude my talk. So first, so in my talks, the focus is the differential characteristics and its probability. But of course, we need to consider differential effects more accurately. Then, unfortunately, we don't have any comprehensive and nice strategy to compute the differential effects. So I think this is an open question. And also a linear cryptanalysis. So actually, as far as I check, so tackling linear cryptanalysis is much difficult than differential cryptanalysis. But we already have something result for LadyPat. So for this project paper, and also other constructions. So now our application is limited to AES-B-MC cipher and EGFN. If we want to focus on other design, we can we need to analyze the linear layer additionally. Okay, so thank you very much for the listening talk.
Okay, thank you, Yusuke. And so we now move to the third and final presentation of this session. The title of the presentation is the parallel verification of serial MAC and authenticate AE modes. And this presentation will be given by Kazuhiko Minematsu. So the floor is yours.
Yeah. Do you hear me?
Oh, yes, I can hear you clearly.
Okay, thank you. Thank you for the introduction. So yeah, this talk is about some simple thing about the serial MAC and the authenticated encryption mode. So let me start with the perhaps the simplest MAC mode, that is a CBC MAC, as you can see here, and it is a block cipher based, and it's a provably secure for fixed message lengths. And as you can see that we only need one block cipher core to process one input message here. So it is efficient in terms of the number of the block cipher. But of course, as you can see, it is completely serial. And we already know a number of the polarizable mode in case of the MAC. For example, we have a PMAC, but such polarizable modes need more state memory. To save the operational state. This implies that we need a larger implementation size at the cost of the being polarizable. So this paper, in this paper, we present a very simple, perhaps very, very simple solution to mitigate this gap, which we named the pincer verification. It is essentially doing a two-power verification applicable to some class of serial MAC modes. And it's a nice thing is that it preserves the functionality and the security. And we also extend our technique to the authenticated encryption mode, a certain authenticated encryption mode. And in that case, we may call it a pincer decryption. And we also show some concrete applications with some implementation result that covers one candidate to the NIST lightweight cryptography standardization effort. And we also applied our result to the two NIST standards, namely CMAC and the CCM. And for all cases, for the decryption or verification, we double the performance. So the core idea is, as I mentioned, it's ultimately simple. So in case of the CBC MAC, in the verification, we have a tuple of M and T here, where M denotes the sequence of these concatenation of these message blocks, and the T is a tag here. And in the normal verification, we start from the top and compute and verify at the tag here. But we suggest that if we have a decryption routine of the block cipher, we just start from the top and start from the bottom here by using the block cipher decryption. And we check we get some state value here in the middle point, and we check if these points are correct for both sides. It is almost trivial to see the functional equivalence of this verification procedure to the regular verification. And we can make it a more formal statement for those, when a MAC mode allows a pincer verification that is correct and equivalent to the normal verification. And we also extend our technique to the authenticated encryption mode. So to do so, we consider a type of the authenticated encryption mode that is inspired by the COFB proposed at 2016. And the encryption scheme is here. This yellow box denotes the tweakable block cipher, and this low function denotes the state transition function that takes two input blocks and output two blocks. Okay. And I'm skipping the detail, but if this class of authenticator mode can be represented by a sequence of two functions, which is an extension of the tweakable block cipher, which we call the TBC auxiliary with auxiliary output. Then this authenticator encryption mode allows two parallel decryption that is functionally correct with a regular verification. And as we have three case studies with three applications. The first one is a ROMRAS, which is a finalist of the NIST lightweight cryptography standardization. The structure is actually similar to the COFB, but it is a tweakable block cipher based, and it uses a skinny tweakable block cipher. And it has a primary member called ROMRAS N, and it can be described as the class of the authenticator encryption mode that I described before. And I'm skipping the detail, but we implemented ROMRAS N on a dual-core 32-bit microcontroller called ESP32, following the quite naive strategy, namely meaning that one encryption core performs the forward pass, the other core performs the decryption backward pass. And we get a desirable result, meaning that we halve the decryption costs for a certain amount of the ciphertext. The second case study is the CMAC, which is a NIST standard MAC mode based on the CBC MAC. And it's mostly identical to the CBC MAC, just a difference is in the Rust block here. And we implement CMAC on Intel CPU having the AES instructions called AES-NI. So in that case, a nice thing is that we can hide the latency of the AES instruction by parallelizing two blocks. The one block performs the encryption part, the second core performs the AES decryption routines. And actually we get an 1.65 cycle per byte on Skylake processor, which is twice faster than the regular verification. And finally, we also present our implementation result for the CCM, which is one of the two NIST standards for authenticated encryption. It's quite widely deployed, and I'm skipping also again the skipping the detail, but then compared to the normal decryption strategy, which was adapted by OpenSSL, which we call it an interleave, which interleave is actually CBC MAC and counter mode. But our technique also even combines provides a better parallelizability by combining the interleaving strategy and pincer verification with CBC MAC. Okay, and this shows the decryption routine where the green box computed in advance. Then we can perform these 4 lines in parallel. Okay, and as a result, we get on the Skylake processor we get the speed of the 1.78 cycles per byte for 1 kilobyte ciphertext, which is again twice faster than the regular CCM decryption by the state-of-the-art method. Okay. In this talk, I present a very simple two-parallel solution to verify or decrypt performing the CDR MAC or authenticated encryption mode, and it is widely applicable to CBC MAC like MACs or COFB like authenticated encryptions. Okay, that is. Thanks.
Thank you, Kazuhiko. So we have spent a bit more time on the presentation in this session. So, but let's keep the question answer session a bit short. And so, any questions?
So to Kazuhiko?
Yes.
So I want to ask one very short question. So I think in this case, so you can't truncate tag.
That's exactly, yes.
So the necessary condition is you should output as a tag directory.
Yes,
Okay,
truncation
thank
is
you.
not possible. Yeah.
Okay.
I actually have a related question for Kazu. Just out of curiosity, because you also applied, say, to Romulus, but if I remember well, Romulus never needs the decryption oracle, also for decryption, right? So,
Yeah.
so if you want to decrypt a ciphertext or authenticate the decrypt, whatever, then you never evaluate the block cipher or the tweakable block cipher in inverse direction. That's correct, right?
Yeah. You mean that yeah.
In the
for
normal
the
way.
regular
The-
number. Yes.
Yes. So now you indeed need this. Does this give a lot of overhead or is it okay?
You mean the implementation or overhead?
Yeah, the implementation overhead of your pincer verification.
Yes, exactly. Yeah, in case of the regular decryption, we don't need a inverse circuit of the tweakable block cipher. But yeah, in our case, we actually need that. May increase the implementation size or code size or yeah, totally.
Okay, I have question to Yosuke. So did you consider your idea, the swapping ideas on gift to have better differential bounds?
One gift?
Yeah.
Gift block cipher?
Yeah.
So now, our idea, our main idea is mainly applied to XOR-based linear layer. So currently, so gift-like design, so the present-like design, I don't have any idea beyond the branch number.
Okay. Okay, thank you.
Yeah.
Any more questions? Maybe I can ask a quick question to Bart. So you are if I remember correctly, you were saying that in the Elephant V2 mode, you have some little bit security degradation. Is that right? Because of the transmission?
I didn't hear you well. I have a little bit different what?
Oh, so yeah, you are saying that in the security bound you have a little bit security degradation because of the nonce misuse.
No, so for Elephant V1,
V2.
Yeah, so yeah, V2, we don't have security degradation. I think what I said is that the security bound is slightly different compared to the one of V1, because now we used to have a Wigman-Cartel proof, and now we have a protected counter sum based proof, which is slightly different, but that's not significant. Of course, you have also a small security degradation in the multi-user setting, but there is also basically negligible. Of course, if the attacker can attack multiple schemes at the same time, even generically, it has a higher success probability of breaking a scheme, but there is no real security degradation.
Okay, yeah, I just wanted to
yes,
I mean, make sure that I understood it correctly. Okay, thank you. So is there any other message? So if not, then I will pass the session to Yusuke for the next session. Thank you. Let's thank all the speakers of the session.
Okay, so thank you very much. So program co-chair, so now 5 minutes is behind schedule. So is it okay to everything 5 minutes in behind schedule?
Yeah, that's fine.
Okay. Okay, so now let's go to the session 2, Symmetric Crypto 2. Okay, we have 4 talks and the same, so each talk have 5 minutes. And after the talk, we have a discussion time like the session 1. Okay, the first session, first talk is related to weak impossible differential cryptanalysis of reduced round 2 AES by Chao Niu, Mizhou Liu, Meijin Wang, Qingju Wang, and Xu Ming Yu. So where is presentator? What? Is there a presentator? Nothing? What?
Yeah, it's a bit weird. So
Okay, so currently maybe we
can leave it at
both?
the end of the session. Maybe someone will turn out.
Okay.
Yeah, all right.
Okay, so change the talk. So the first we go the second talk. Improve the attack on Gift 64 by Linsun, Wei Wang, and Meijun Wang. So maybe Linsun. Okay, thank you very much. Thank you, Lin.
Okay, can you hear me?
Yes, I can hear better. You. Oh, okay. Now I can check your slide. Okay.
Okay, thank you. Thanks for the introduction. Hello, everyone. The name of the presentation is Improved Attacks on Gift 64. Gift is a lightweight block cipher motivated by present design strategy and has significantly reduced linear high effect. For the good performance in implementations, Gift acted as the underlying primitives of many lightweight designs. When we investigate the security of Gift 64, we find a few works consider the security of the cipher regarding the linear attack. More precisely, apart from the study of the 9-round linear high effect, in the design document, we found no linear attack result. At the same time, the previous 20-round differential attack demanded the full code book. So, motivated by these observations, we aim at improved linear and differential attacks on the cipher. And we think this will promote a comprehensive perception of the soundness of Gift 64. The contribution of this work can be divided into four parts. To facilitate the selection of linear and differential distinguishers in attacks, we estimate expected linear potentials of a lot of 12-round linear approximations and the probabilities of many differentials. Then, benefiting from the good performance of the newly detected distinguisher, we propose the first 19-round linear attack and the first 20-round differential attack without using the full code book. The selection of the linear distinguisher can be divided into 3 steps. In the first step, given the weak linear high effect of Gift 64, we set the length of the linear distinguisher as 12 rounds. Our goal is to implement 19-round linear attack. We apply the set solver to exhaustively search for all 12-round trios with correlations being 2 to the minus 31 and obtain more than 5,000 of trios in total. Then in the second step, we evaluate the number of sub-k bits GSBL of all candidate linear trios. As shown in the figure, since all trios have small values of GSBL, so they all have the potentials to launch valid 19-round K recovery attacks. Then in the third step, we turn our attention to the ELP of the linear approximation containing the 5,120 trios. Due to the considerable number of linear approximations, for each candidate, we can only exhaustively search for all trios with correlation larger than 2 to the minus 40 and give approximate estimations for the ELP. This table shows the distribution of the number of linear approximations with different GSBL and ELP. The experimental result enables us to fix the distinguisher in the attack as L16, which has the minimum value of GSBL and a relatively high ELP. Similarly to the case in the linear setting, in the selection phase of differential distinguisher, we try to find 13-round distinguisher so that we can improve the previous differential attack. Accordingly, our goal is in implementing 20-round differential attack without using the full codebook. The second step is to search for candidate differential distinguisher. Since the trio with probability greater than 2 to the minus 64 do not enable us to realize a valid attack, we lower the objective probability to 2 to the minus 64 and obtain more than 90,000 of trios. In the third step, for each of the trio surviving in the second step, we analyze the number of sub-K bits GSBD involved in the K sub K enumeration phase of the differential attack. The result is shown in the figure. A rough investigation shows that the 3000 and the 96 trio with GSBD strictly less than 112 are qualified for 20-round valid differential attacks. Then, after controlling the time complexity of the attack, in the fourth step, we focus on the probability of the distinguisher. We use the set solver to search for all differential trios within each differential with probability being larger than 2 to the minus 71. The distribution for the number of differential with distinct probabilities is listed in the table. With this result, we narrow the range of candidate distinguishers to 32 differentials with probability being 2 to the minus 61,313. The distinguisher in the final differential attack is D3 highlighted in this table. It has the maximum value of differential probability and the minimum value of GSBD. This table gives a summary of cryptanalytic results on GIFT64 to date. Note that the 19-round linear attack in this work is the first linear attack result on the server, and we also give the first 20-round differential attack without using the full codebook. Given the newly obtained results, we conjecture that the resistance of GIFT64 against the differential and linear attacks do not have a significant gap. Also, we note that the attack results in this paper are far from threatening the security of GIFT64. That's all for the presentation. Thank you for your attention.
Okay, thank you very much. So the question is after the session, so we need to go the next talk. Next talk is a simpler model for recovering superpoly on Trivium. This is a paper by Stephanie Delam, Patrick Davis, Arthur Gontier, and Charles Prudhomme. And the talk is by Arthur. Okay, please.
Okay, so can you hear me?
Yes.
Okay, so I will briefly present a simpler model for recovering superpoly on Trivium. So first, for some context, we here are in the cube attack. So in the cube attack, if we have a stream cipher as a function f, we compute the sum over all the possible values of a chosen cube of this function f, and it reduces to a polynomial named the superpoly. And the main goal of a cube attack is to recover the superpoly. The previous method uses a bitwise constraint to model this problem to find all the monomials of the superpoly. And in this paper, we propose a graph-based model that focuses on the interaction between the bits instead of the bits themselves. So to build this graph model, we first model Trivium into an automaton with the 3 registers of Trivium A, B, C. And we have 4 possible transitions for each register, 1 looping transition, and 1 transition to another register, the small transition, the doubling transition, and the big transition. And we can see that Trivium has a very specific structure because the long transition is always 1 shift more and 2 shifts more than the doubling transition. And so this will lead to some doubling patterns. So for example, in this case, I have 2 configurations when if I take the long edge in red here on the left or the doubling edge in red on the right, I will end up to the same leaves. So this means that if in my graph model I have one of these 2 patterns, I can constrain it because by replacing the red edge by the other possibility, I will have the same leaves. And since we are searching for a polynomial, if we have an even number of solutions, which means an even number of times the same monomial in the polynomial, since we are in F2, the monomial will cancel themselves. So we want to find all the solutions, but for each monomial, we want to know if there is an even or an odd number of solutions. And constraining these patterns will cut from the solution pool a lot of even solutions. But there is a problem for these patterns. The problem is when the patterns are overlapping. So for example, here, if I constrain the 2 first patterns with the red edges, and then I constrain the two patterns on the bottom with the red edges also, I think that I have canceled 4 patterns, but in fact, I canceled only 3 because the 2 left patterns are exactly the same. So we can't do this because we will break the parity and we won't find the good superpoly. So we have to take into consideration the pattern overlapping, and this can be a really hard question when we have multiple patterns to take into consideration at the same time. The second improvement we provide with our paper is the strategy. The Trivium models, the previous Trivium models were really big, and the solver could not solve it with its basic strategy. So the previous papers uses some strategies like hot restart or divide and conquer. They cut the first part of the problem and then they solve all the subparts. But we show with the graph model that we can use some previous work on the arity approximation, the arity of the cube, and we can use this approximation as a solver strategy to directly tell the solver we want to focus on the doubling edges of the problem, because we know this is the hard part of Trivium, and the big arity edges first, because with the more arity on the edge, we know that we most likely end up to a solution. So once we set up this strategy into the solver, then we didn't need any cut, any divide and conquer strategy. So in the end, we have a MILP implementation of our graph model that is consistently faster than the previous method, like monomial prediction and division property. And with our doubling constraint, we find far less solutions, far less even solutions than the previous methods. And we know that if we could use more patterns, then we could even more reduce this number of solutions in the table at the end here. So as a conclusion, we propose in this paper a new graph model to model a Trivium, the recovery of the superpoly of Trivium. This graph model enables the using of doubling pattern as constraint to reduce the number of even trail. It enables the usage of arity approximation as a solver strategy to reduce the solving time. And at the end, we have a faster MILP model than the previous method with less even trails. The questions we are raising are how to prevent the multiple pattern overlapping. In our model, we are using only one pattern with one overlapping. But if we use multiple patterns, we have the problem of multiple pattern overlapping, and we think this is a really hard question. We could also strengthen the solver strategy with other trivium features than the arity approximation. And we could also apply the graph method on other ciphers. Thank you for your attention.
Okay, so thank you very much for the. Let's go to the next talk. Automated truncation of differential trade and trade clustering in ARX by Alex Birkhoff, Juan Carlos Santos, Daniel Feyer, Veselin Berishov, and Giuseppe Pito. So please.
Hello, can you hear me?
Yes, I can hear.
Okay, thank you, Yosuke. Thanks for the introduction. This is joint work with Alex, Luan, Daniel, and Giuseppe. So one of the main contributions of our work is an automated tool for automatically truncating differential trails for ARX ciphers. And the slide illustrates the main idea behind the tool. So it takes as an input a fixed input differential trail, and it produces a truncation of this differential trail shown on the right. So here the trail is represented in terms of differences given in binary. And for every round, you have the inputs and outputs to the modular addition. So this 3-round trail assumes a hypothetical cipher that has a single modular addition per round. From an initial trail with probability 2 to the minus 7, we obtain a truncation that has probability 2 to the minus 5.16, which inside of it encodes 16 non-truncated trails. And each star symbol in the truncated representation implies that the bit can either be 0 or 1, and for any assignment, the resulting trail is valid. This automated truncation is made possible due to carefully controlling the propagation of star bits through the rounds of the cipher. And to do this, we define 2 sets of rules, simple and relaxed rules. So for the simple rules, they only take into account linear dependencies between star bits, and they make it possible to compute the differential probability of a truncated trail in linear time. And they also make it possible to merge multiple truncated trails that are possibly overlapping into non-overlapping sets. Now, the limitation of this set of rules is that they don't capture the full signal. So they may be simple, but they don't capture the full signal. So we propose a second set of rules, relaxed rules, which are slightly more complicated because they take into account also nonlinear dependencies between star bits. But because of that, they capture significantly a larger fraction of the signal. At the same time, the price that we pay for this is that there is no efficient computation of the differential probability of truncated trails based on these rules. And also, it's not possible to easily merge truncated trails based on the relaxed rules. The ability to construct this kind of truncated trails allows us to build distinguishers with low data complexity. So we give an example for spec 64, where we report an improved truncated trail distinguisher for 15 rounds. And it is composed of 15 non-overlapping truncated trails that encode 112 non-truncated trails. Of those, 22 trails have a cumulative probability 2 to the minus 59 0.5, which results in a distinguisher that requires approximately 8 times less data compared to the optimal, compared to a distinguisher built on an optimal trail. that has probability 2 to the minus 62. So this kind of so these distinguishers based on truncation and clustering should be applied with care, because naturally the larger the set of non-truncated trails encoded in a given truncated trail, the higher the probability of the truncated trail, of course. But at the same time, the higher the probability that there may be a random match within this large set of trails. This is precisely the reason why, for this particular example, we have to take 22 out of the 112 non-truncated trails in order to make sure that we still maintain signal-to-noise ratio bigger than 1, and therefore can still apply the distinguisher efficiently. In fact, it's arriving at a good trade-off. It's quite tricky, and we provide rigorous statistical analysis for this in the paper. We further improve the reported distinguisher on spec by applying more heuristic techniques and SMT solver. So in particular, we take the 15-round optimal trail, and we try different divisions of this trail into sub-trails. So basically, we divide it in 3 parts, and for each of them, we employ an SMT solver to approximate the differential probability of each of the sub-trails. And we obtain the best result for a division of 3-12-3, so K and J, which results in a distinguisher with probability 2 to the minus 55.029, which encodes 389 unique input-output difference pairs. And a final question that we investigate in our work is whether the best cluster obtained in the described way is always obtained from the best differential trail, so from the optimal trail that we know. And the answer is no, because we are able to find examples in which clusters which are obtained from suboptimal trails in terms of probability actually result in better truncated distinguishers in terms of probability again and signal-to-noise ratio compared to clusters built around the optimal differential trails. And on the slide, and the red line shows a cluster that is growing around an optimal differential trail, while, for example, the rightmost curve is built around a suboptimal trail, and as you can see, at some point it climbs above the red line, indicating that the probability, in fact, increases of this suboptimal cluster. So, to a very brief summary of our results. So we propose a tool for automated truncation of differential trails in ARGS. We report improved distinguishers on spec 64 reduced to 15 rounds with associated analysis, statistical analysis of the distinguishing advantage of such distinguishers. And finally, we investigate distinguishers obtained around suboptimal differential trails. Thank you for your attention.
Okay, thank you very much. So now, okay, so the first talker joined this session. So, okay, so the last talk is a related tweak in possible differential cryptanalysis of radius land 2AS. So maybe, okay, yeah.
Hello, can you hear me?
Yes.
Thanks for your topic we are going to discuss today is a related tweak in possible differential cryptanalysis of reduced round 2AS. And my name is Chao Niu from Shandong University, China. And thanks for your introduction. 2AS is the underlying primitives of authenticated encryption with associated data scheme estate, which was accepted as one of second-round candidates in the NIST lightweight cryptography standardization project. Multitude 2AS is a tweakable variant of AES-128, and it is identical to AES-128, except that it just injects a 4-bit tweak every 2 rounds. AES is a well analyzed cipher, which means we have strong confidence in its security. The best attack against AES 128 in the single key setting only reaches 7 out of 10 rounds. Compared to AES 128, the tweak AES just adds a 4-bit tweak. So we're interested in the security of tweak AES. We're exploiting the property of tweak AES, mainly the influence brought by the 4-bit tweak. And we found some mistake of the impossible differential attack in the design document. This attack, and the time complexity exceeds the exhaustive search. Then we proposed a new 8-round key recovery attack with a valid complexity using a 5.5 round distinguisher. Next, we will introduce impossible differential. At our original cryptanalysis, we usually use the miss in the middle approach. We denote the difference on the plaintext X, alpha, and the difference on the ciphertext beta. Then we propagate the difference on the plaintext in the forward direction and the difference beta in the backward direction. When they meet together and a contradiction occurs, then we find an impossible differential. Next, we will introduce the property of add tweak operation in the tweak AES. Here we can see the beginning of the 6-round distinguisher is equal to the tweak difference. Then we propagate this difference, an inverse AES round. Then we can find the involved key bit is the main diagonal and the diagonal below the main diagonal in the K1, subkey K1. And then we propagate the difference on the end of the distinguisher. We can find the involved key bits on K9 is 0, 3, 6, and 7. Then in this case, we can find the involved key bits is different from this case. So we cannot use a different tweak difference to implement one key recovery attack. So we try to find a new distinguisher to implement our 8-round key recovery attack. So use this distinguisher with a tweak difference on the beginning of the distinguisher and only one byte active at the end of the distinguisher. We can implement a 8-round key recovery attack. Thanks for watching.
Okay, so thank you very much. Okay, so now we go to the question time. Sorry, what is this question? So the Waston Lad?
Yeah, so this is for the most recent speaker. And my question is, how does your tweakable version of AES compare to applying the XOR encrypt XOR mode to AES?
The tweak AES is is different from AES 128 that it injects a 4-bit tick every 2 rounds at before the key set the AES key addition. In this picture, we can find the original AES 128 is a sub-bats, shift row, mixed column, and add key. But in 3AS is at the add key operation, we add a 4-bit tick into the state every 2 rounds. So this is the only difference between the two cipher. So when we investigated this operation, this property of add tick. Thank you.
Can I add a comment on your
of course.
question? Yeah.
Yes,
Oh,
of
yeah.
course.
To my understanding, this 3AES is a dedicated construction, so that it means
Yes.
it's designed to achieve a full security, while the XEX is a mode of operation, and it's a birthday secure, means that it's allows only to the half of n bit plain text or ciphertext pairs. So that's they are aiming at different security goals, to my understanding.
Thank you very much. Yes, I also agree with your opinion. So what song is it okay for you?
Yeah, that answers my question.
Okay. So do you have other question? Okay, so I have one question to Link. So improve the text on gift 64. Okay. Maybe I think okay. Okay, so I'm not sure I can understand perfectly. So maybe you enumerate many linear trails and you estimate the linear Hall effect to compute the expected linear probability. Is it right? Oh. Lin, can you hear me? Oh. Oh.
Hello.
Hi.
Hello. Oh,
okay.
Sorry. There is something wrong with my earphone. So okay. Can you repeat the problem?
Okay. So maybe when you estimate expected linear probability, you enumerate many linear trails.
Yeah.
So how do you evaluate the impact on the sign of each correlations of linear trail? Maybe when you estimate linear Hall effect, so some trail has a positive and some trail is negative, then there is a possibility as a correlation is cancelled out. So how to handle this?
We only use the expected linear potential, and the definition of expected linear potential is quadratic sum of linear correlation of every trail. So we do not consider the sign of the linear correlation.
But you now sort of fix the input mask and output mask, and you animate many trays.
Yeah.
Then, of course, so that in general, so the more accurate, if you want to estimate more accurately, you need to consider the impact on the sign of each correlation.
Yes, maybe we can do it
Okay,
in the future.
Okay, I understand. Thank you very much.
Thank you.
Okay, so do you have a question?
Okay, I think if there are no more questions, then we should slowly get into the break, because according to plan, Sophia's talk was supposed to start in 3 minutes. So I would say we take a 5-minute break so that people can grab a coffee or something cold to drink, depending on where you are on the planet. And we start with Sophia's talk at 25.
Okay, so thank you very much.
Thank you.